Welcome to another episode of Yummy Data Science. In this episode, I'm going to be talking about predicting readmissions with logistic regression. So let's get started. A little bit of context. Why is it important to have machine learning models to predict probability of readmission? Well, the idea behind why we want to have ML models is to take preventive action so that the predicted readmission does not take place. And obviously, hospitals have an incentive to do this, as do payers, and it is great for patients. Uh, and you could do it at 2 points. You could do continuous ML scoring as new data comes in, or you could do the machine learning model scoring at the time of discharge. So let's think about uh, predicting the probability of a readmission with logistic regression. And if you have never heard of logistic regression, that's okay. If you've heard of a linear regression, then let's think about it in that way. Well, one of the things about a linear regression is that you're predicting something that is a continuous variable. So you might be predicting income, and your explanatory variable might be education. So you hypothesize that if a person has higher and higher levels of education, their income will go higher and higher. So you might be saying their income would be a continuous variable. Maybe it would be from 10,000, so like $100 million. So income is a continuous variable. And you'd probably be saying, okay, education and other things are also continuous or discrete variables. The explanatory variables, it doesn't much matter whether they are continuous or discrete. They can be a combination. But the idea behind linear regression is that the predictor is a continuous variable. Another example, in the healthcare arena, we might say, well, let's predict hospital length of stay. And the explanatory variables would be diagnosis, comorbidities, socioeconomic factors, etc., the geography. And then the predicted length of stay would be a continuous variable, like 2 or 5 or 8 or 10. But the main problem with predicting readmissions with such a framework is that readmission, it's either a yes, it happens, or it's a no, it doesn't happen. So it's discrete, it's a 0 or 1 outcome. And here in the graph, let's pretend that this is readmit on the y-axis. Yes for it's a readmit, no for it's not a readmit. And let's say this is purely a function of age. And our hypothesis is that the older people are more likely, as our data can tell you, are more likely to have readmissions. And younger people are less likely. So you look at this graph and you say, okay, maybe there's some point around this age. So if they are more than 50, you can say they're going to have a readmission. If they're less than 50, they're not going to have a readmission. So if you were to do a linear line on this, you would get a straight line, like the red line. And the problem with the red line, it's actually not so bad. Some economists and healthcare economists have argued that it's not so bad, the red line. But the problem with it is that it can take on values that are less than 0 and more than 1. Okay, and you see this right here. So what we need is a function that bounds the output of the regression to the upper cap of 1 and the lower minimum of 0. So what we really want is an S-shaped curve. And if you stare at the blue dotted line hard enough, you will imagine that it's an S. So the point of the slide is that a linear regression violates the 0-1 nature of the predictor variable because it can output, it can predict below 0 and greater than 1. And so what we need is this S-shaped curve. So what we really need is a link function. And that link function is probability that goes from 0 to 1. And you can say 0, 1, 0.1, 0.999, etc. So this link function is a probability and it's a function of z. And z then is going to be continuous. Z could be anything. It could be negatives, it could be positives, but P of z would always be bound between 0 and 1. That's what we want. So consider that you have a bolt of lightning and you just inspired by pure genius. And you say, I got it. There are two mathematical equations that take z from a continuous, so minus infinity to plus infinity. And these two equations are actually the same. And you have one equation, e to the z, divided by 1 plus e to the z. And then the other equation, which you know because you had this bolt of lightning and inspiration, you know that 1 over 1 plus e to the minus z. Okay. And now you have, because you have had this bolt of inspiration, you know that this is bounded. Okay. Okay, how many of us realistically have these lightning bolts of inspiration and we imagine functions that have e, z's and e minus z coming out of it? Very few of us. So let me kind of give you a very intuitive high level understanding. First, I want to tell you that these equations 1 and 2 are the same. How? Well, just think about equation 1. And let's say you start by multiplying the numerator and the denominator by e to the minus z divided by e to the minus z. And that's just 1. So you can multiply the denominator and the numerator by 1. You know you can do that. So if you multiply the top by e to the negative z, you get e to the z, which was the original numerator. Then you get multiplied by e to the negative z. And the nice thing about this exponents, z plus z and negative z, is that they add up. You can add them up. And that adds up to 0. And we know that anything raised to the power 0 is 1. So we know that the numerator will be 1 and the denominator will be 1 plus e to the minus z. And if you don't believe me, just get a piece of paper and a pencil and work it out. So the point of the slide here is that we have a link function that takes z that is continuous from minus infinity to positive infinity. And we have seen two mathematically the same variations of this function. And now we're going to go ahead and talk about the logistic regression. So let's think about what this link function does. Okay, and I've put the first equation and the second equation on the same line. Well, consider equation 2. It's the more non-intuitive, but it helps when you are thinking about z ranging from negative infinity to positive infinity. So consider equation 2 when z is negative infinity. So it's a very, very, very big negative number. Okay. Then e to the minus minus z, the minuses will cancel out, will approach infinity. So the denominator approaches infinity and this whole equation approaches 0. Okay. So we know that when z is negative infinity, our p of z approaches 0. Well, good, because we want to restrict it from 0 to 1. The second scenario is when z is infinity, e to the minus z approaches 0. So the denominator approaches 1 and 2 approaches 1. Nice. So we achieved our objective function. P of z, the probability of z, is restricted from 0 to 1. Okay, how do we interpret z? Well, z, now we can think about it in our same old, the way we thought about a linear regression. Beta naught, which is the intercept, plus beta 1 times x. And here you know that you can have more than one explanatory variables. You can have beta 1, beta 2, etc. And the interpretation of z is that it represents the log of the odds ratio. This is a mouthful, so I'm going to break this down. Log of the odds ratio. But first I want to mention that beta 1 then is the log of the odds ratio of 1 unit change in x. And let's just keep that in mind. But now what we're going to do is try to see why z is the log of the odds ratio. Well, you can think about that, and I know I'm not being mathematical at all. In fact, mathematicians would cringe and should cringe at my explanation. So let's substitute log of the odds ratio for z in our equation 1. Remember, we said they are the same, equation 1 and 2. So if you do that, then e to the log of the odds ratio, because e and ln cancel out, then what we get is probability of z is the odds ratio divided by 1 plus the odds ratio. But wait a minute, that is the definition of probability. Odds ratio divided by 1 plus odds ratio. Now, if this has left you more confused than ever, listen to the next part. There is a direct translation between odds ratio and probability. Let's say I tell you that the odds of your being successful are 4 to 1. That means if you played the game 5 times, 4 out of the 5 times, you would be successful. So what are the odds? 4. 4 to 1, right? We don't write the 1. What is the probability of success? 4 divided by 1, right? 80%. Now, 80% can also be written as probability divided by 1 minus probability, and that's the odds. So we have proved that P of z is the odds ratio divided by 1 plus odds ratio. So then, if you think about what we started with, we have now shown in a very mathematically lax manner that z represents the log of the odds ratio. Well, how do you compute predicted probability? Well, the way you do that is you take your rho, you take the explanatory variables, you take the coefficients that you've gotten from your logistic regression, you compute z, and then you plug it into the probability of z. And here I have used the first equation. So let's say that I have patients A and B, and patient A was readmitted, patient B wasn't. Patient A was 22, patient B was 38. I centered their age because age is 30, so I centered it. And this is minus 8, and this is plus 8. Now, they can have a diagnosis of mild, medium, or severe. So this person, patient A, had a diagnosis of severe and was a male. And so the probability of prediction by the logistic model is 0.89. And you can see that this is pretty close to the predicting the real thing that happened. and he was readmitted. He or she or they were readmitted. Now, in the second case, both the diagnosis medium and diagnosis severe are false. That means they're the diagnosis of mild. This is not a male, and the probability of readmit is 0.09. And this is pretty good because the readmit didn't happen. So the way you figure out predicted probabilities is you first compute Z. And for A, Z was computed to 2.14. Then E to the Z is computed to 8.5. That's the odds. And then you plug in the formula to calculate P of Z, 0.89, and came out to be exactly what the logistic regression did. And for patient A, you can think about it. B2 is the intercept, so you take that, plus G2 is the age centered, so minus 8 times 0.04, which is the coefficient for the age, plus B4, which is because their severe diagnosis was true, and then B5, which is that they were male. Okay, so it's just a very simple calculation. And in this slide, I have proved how you compute predicted probability by first computing Z and then plugging it into the formula. And I verified that my logistic regression output gives me the same. Okay. Now, here is a difficult question. You say all this is wonderful. We had the bolt of lightning. We came up with these two equations. We proved that they're the same. We know what they represent. We know that the Z, P of Z, Z then represents the log of the odds ratio. But you're like, well, how am I going to compute the intercept and the beta 1s, the parameters? Well, if you know a little bit about how linear regression is computed, it actually doesn't matter because this method is different. And this method is called something like maximum likelihood estimation. And if you have gone through textbooks and watched YouTube videos and you don't understand, never fear, just hang on for a few more minutes. I'm going to try to give you a very intuitive, non-math explanation. The basic concept of maximum likelihood is this. Given the observed data, what parameters of Z maximize the likelihood of observing the data? And when things are difficult, I really like to simplify them. So I'm going to say we only have two patients A and B. So, and let's take two cases. In one case, Z is 0. And in the other case, Z is what our model gave us. So I'm going to figure out the likelihood of observing patient A and patient B's data given Z is 0. How am I going to do that? Okay, step 1. If Z is 0, then E to the Z is 1. So the probability of Z is 0.5, no matter what. If Z is 0, the probability is always 0.5. Now we know that patient A's likelihood is the probability of Z times if they were readmitted plus 1 minus the probability times if they were not readmitted. Well, patient A had a readmit, so we know that the first is going to be 1 and the second is going to be 0, so it will cancel out. So this will be 0.5. The second patient has the same likelihood, except in this case, they were not readmitted. So the first terms cancels out to 0 and the second term becomes 0.5. And then you can imagine that patient A and B's likelihood together is 0.5 times 0.5 is equal to 0.25. So very relaxed likelihood function of seeing patient A and patient B's data given that Z is 0, 0.25. That's the function. But we know that we can do better than z is equal to 0 from our parameter estimates of z. So let's see how this works out. Well, given z from our model, what is patient A's likelihood? Well, it's simply probability of z. Readmission is yes. And that was 0.89. I just copied it from a slide, 2 slides back. So 0.89 times 1. And the next term, 1 minus p of z, is 0.11, but this will cancel out. And then the second person is the same. He had a probability 0.91 of not having a readmit. And he didn't have a readmit. So now this is 0.91. And if I put the two together, 0.89 times 0.91 is 0.81, which is much higher than 0.25. So the main idea behind MLE is this. Choose your parameters that maximize the likelihood of observing the data. And we tried with z is equal to 0, and we came up with 0.25. And then we tried z, where the model parameters were equivalent to what the logistic regression results were. And we saw that the likelihood function was much greater. So I hope this makes intuitive sense to you. The last thing, for those of you who are mathematically inclined and are likely to think about this as they are reviewing logistic regression output from Python, is this. There are two considerations when we are doing MLE. First, it's mathematically easier, instead of maximizing something, is to minimize the negative of it. So we minimize the negative of the likelihood. Then calculus is the branch of math that deals with what is the rate of change. And to find the minimum, you want the rate of change. You want a rate of change to be something. Okay? So you're going to be doing calculus. And it turns out that our likelihood function, you saw the probability of A and B together, we multiplied it. But it turns out that it's easier to do calculus with addition rather than multiplication. So what we end up doing is we use a construct with logs. And in log, if you do log, you can think about it as addition. So in reality, when you say you're really minimizing the log of the negative likelihood function. And now I'm pretty much done, and I want to quickly show you these results in Python. So if you've listened so far, my kudos to you, and I hope you've learned something. I'm showing you my Google Colab notebook, and the first thing I'm doing is I'm reading in the readmits file I made last time. And then I'm also reading in the member file that I made. And what I'm trying to do is I'm trying to get some more characteristics from the member file. So I'm joining the member and the readmits file by BenAID and year. But then I also do some checks. For example, I need to check whether the BenAID can appear in 1 year twice. So I do them. And I'm using a lot of the coding that I do it using AI, and I'm in two minds about it. Sometimes AI can be very good at the easy stuff, but at the complex stuff, it can actually add to my time and frustration. So, yeah, I've had second thoughts about where I'm going to use AI, and I've decided I'm going to use it in simple cases. Okay. So I have their enrollment counts. I have their now I'm ready to do logistic regression, and I've got my BenAID, I've got my DRG, I've got my principal diagnosis code, I have the readmit flag, I have the birth date, I have the sex, I have the race, I have whether they have ESRD, which is end stage renal failure. I know how long they've been enrolled, etc. But I investigated these results, and because they are synthetic, I didn't see a signal. And so again, I debated with myself, should I show results that don't make any sense? Or should I go ahead and do a little bit of cheating or inventive teaching? So what I did is I did a big switcheroo with the Titanic data set, and I renamed some columns. And now I'm going to be um, um, looking at readmissions, and I'm going to be looking them as a function of diagnosis. So 1 is mild, 2 is moderate, 3 is severe. I'm going to look at it as a function of sex, and I'm going to look at it as a function of age. So then I do logistic regressions. Um, so now I'm looking at the output from my logistic regression, and I can see that the model is definitely much better than the null model. And the null model in this case is if we just had the intercept, we didn't have any beta ones. And so you can see that the log likelihood and the log likelihood of the null model. And here, this is a little bit tricky because in my previous slide, I talked about minimizing the log negative of the log likelihood. But this is what this is telling you about the goodness of fit. So don't be confused by that. There are some programs which will give you the value of the negative of the log likelihood, but this is telling you about the goodness of fit. And what this is saying is the goodness of fit for the log likelihood with the estimates of the beta ones is negative 323, which is higher than an intercept only model. And then the additional benefit of the log likely of is this is a very big number. So this model is definitely a beneficial model. And these coefficients are the log of the odds ratios. And we have worked with these in the previous slide. I've shown you these in the intercept and the coefficients and how z is estimated. And the point I'm making is I'm taking the exponent of the coefficients and I'm converting them into an odds ratio. So, for example, if you are a male, then you have 2.5 higher odds of a readmit as opposed to, say, not a male, the reference category. And here I'm adding the predicted probabilities to the model. And then I used what I'm showing in cell 16 is that you can use AI to say, okay, how do you predict computed probabilities? And then it did the linear, it did the predictor. So it did all the multiplication for me instead of my having to do it in Excel. And it was just kind of affirming. But this is not a rocket science. So again, I hope that you've learned from my explanation of logistic regressions. Thank you for listening. Next time we'll deal with another algorithm such as decision trees to classify this data. Thank you.